Hello, welcome back, where we are discussing the technique which can be abbreviated as CV, which is cyclic voltammetry. It is a typically known as cyclic process, because we scan one potential and then we come back to the original potential, that means the zero potential if we start from the 0th level. So, how we measure these things, and two already we have defined. One is your working electrode, another is your reference electrode. And as we all know that when we construct a half cell, and there if we consider that consideration of this half cell, we need one electrode, and when we get the other electrode, so you have the corresponding values for the cathode and the anode. So, one is cathode and one is anode, and we all know from the corresponding difference, that means the E right minus E left will give you the corresponding potential for the E cell. So, these were all very much useful for your potentiometric measurements when we measure the E values. Now, we are trying to measure the I values, the current we are measuring, and this current also not at constant potential, what we have seen for the corresponding one for the charge transfer, that charge is being carried out for your coulometric estimations also, which is potentiostatic, that means you have the fixed potential. Now, this will vary, so is a typically a continuous process, and that is why this technique is very useful, that your potential will vary, and with respect to that variation in the potential, how we can determine the corresponding change in your current. So, that the change in the current is very much required to have that particular type of plot. So, current versus potential will be plotting. So, these two electrodes we have, so cathode and anode, and if we consider that okay fine, we have two electrode system and we know that it can be within the cell, you have the cell outside, and if you consider that one of them will be your working electrode and another will be your reference electrode. But to do so, to know that corresponding potential of the working electrode should be monitored, because whatever we plot and whatever we get as the plot, because this particular plot will be getting, and where your E will be there, and E is basically the corresponding potential versus something, it can be respect to your saturated calomel electrode or the corresponding silver chloride silver electrode, or you can directly consider it for normal hydrogen electrode. So, you have to scan this potential with respect to this, that means these two are engaged. So, working electrode is engaged with Re to get this particular potential of this E, and one of the condition we imposed in our previous class, that we should not pass current to this reference electrode. So, how to short circuit the situation, how to pass the entire current through the cell without taking the help of your reference electrode and this two electrode combination. So, we have to have something, that means we can, whether we can bring another electrode or some other arrangement, that we will see. Before seeing all these things, what we can see also, that how we can modify these electrodes for your cyclic voltammetric measurements. So, modification of electrodes can be done in all different ways. One such modification is that based on the miniaturization, that means making the electrode to a very small one, like a needle like electrode. If we can have a needle and that the size of the needle is only several micrometers or nanometers or picometers, so that needle can be inserted on your hand also, and it can reach to your blood level also, and if you can monitor externally with something, so that can be your typical needle like micro electrode, which can be useful for handling your biological samples like serum or blood. So, that we will discuss when we talk in terms of your bioelectrochemistry, but here we will see that how we can modify the surfaces. The electrode is small, it can be your micro electrode, but still we can go for the modification on the surface. So, irreversibly the absorbing substances with desired functionalities. So, you have the adsorption and you attach something such that your adsorption will be more, or sometimes covalent bonding of components to the substance. That means the substance, the molecule what we are looking for their electroactivity can be attached covalently to the electrode surface. And we know that we can have a gold electrode also. The gold surface is very much known for its attachment to the thiols, the sulfur groups. So, you can have a monolayer of some molecules, sulfur bearing compounds on the gold surface, that we call sometimes as self assembled monolayers. That is a very small or thin layer, and we call it as a monolayer, which can considered as SAM. So, self assembled monolayering is possible on the surface, and sometimes we can coat the electrode also with polymer film. That means your electrode is dipped into the polymer and with sometimes with some other substances. That means you can have any Teflon bead or any carbon bead or a carbon disc, and you can modify the surfaces with some adsorption of molecules or some other good species like what we try to measure for their electroactivity. Because what we require is that this particular attachment of the molecules, the molecule itself is not functioning as a catalyst, but it can show some electron transfer catalysis through a mediator like arrangement or a mediator like behavior. That means through this attachment, and if you put some potential to the electrode, that molecule which is attaching to this particular electrode can show either oxidation or reduction. That means it can go for electron transfer reaction, and as a result it can show sometimes the electrocatalysis. That means the catalytic cycle which is attached to that particular molecule or the species which is attached to the electrode through some polymer film or anything else. So, there are also, that is why some electrodes that we will see also that sensors, because this designing these electrodes are very much useful, and we can have some good electrodes, because we just now discussed that hanging mercury electrode or the dropping mercury electrode. So, this dropping mercury or hanging mercury electrodes had been discarded from the very inception by the corresponding polarographic technique, has been modified to go for carbon type electrode, solid state electrode, carbon electrode, platinum electrode, graphite electrode, and all these. So, if you have electrode which can be useful for reducing oxygen to water, can be used in fuel cells and batteries also. So, one challenge is that how you produce oxygen from water, but this is a reverse one, where we can have oxygen from air or any other source, and that oxygen can be reduced for a 4 electron reduction step to get water molecule, and that particular one can be useful for the methodologies that we will see, that fuel cells or in batteries. And extension of that we will also see that the microbes can be useful. The microbes can give rise to the energy which can be termed as microbial fuel cells, MFC, microbial fuel cells, that we will see afterwards in our next class probably, that how we can use this as fuel cell and sometimes that batteries and all, because these microbes what is formed in water, can be river water, can be sea water or any stagnant water, and that microbes or these microorganisms can be given you the corresponding energy in terms of electron transfer and giving rise to burning of the carbonious matter to carbon dioxide and water, and can give energy to your fuel cell. And sometimes these electrodes can be also useful for making electrochemical devices. What is electrochemic? That chrome you know, that is the changing in color due to electron transfer. So, electron plus chrome, that chromic that means the color change. So, electrochemical devices are nothing but it can give rise to the change in color due to oxidation or reduction of the material, and we can have some displays. That means, if you change the corresponding potential of that particular display, it changes its color, that we see nowadays, that electronic display boards or billboards we call. So, those can change color depending upon its corresponding electron transfer reaction, whether it is going for oxidation or reduction. And some smart windows, that means darkening of the window when you have to shield the typical entry of the daylights. So, this will be very much useful, but there within that particular window or the billboard you have the typical electrodes, because all these are has been miniaturized. That electrodes you have in terms of a working electrode or in terms of some filament that we get in lights. So, these electrodes can be charged with the corresponding potential, and we see some change in terms of its color or in terms of its darkening. So, we try to develop with these electrodes also analytical sensors. Sometimes these can also be considered as bioanalytical sensors. How we can prepare those? For particular specimen or functional groups we can attach, and this can be very much useful for sensing some analyte. Suppose we try to develop a glucose sensor. So, how we develop that particular glucose sensor? So, we must have to for attachment for something, a particular species or functional group, or sometimes the enzyme. It is the enzyme which we know as the glucose oxidase. So, if we are able to attach that glucose oxidase to this particular electrode, that will be functional in terms of its electron transfer to the glucose molecule, such that the glucose molecule can be oxidized to gluconic acid, and we can have something, that means if we use oxygen for its oxidation, that oxygen, that means the dioxygen molecule, here we have seen the electrodes capable of reducing oxygen. So, this thing here we correlate it with some sensor which is your glucose sensor. So, here we are reducing oxygen, it can be sensing oxygen, that we know that the oxygen sensors are also available. So, from one point it is oxygen sensor and another point it is the corresponding glucose sensor. So, we can develop these analytical sensors in that way that glucose can be sensed by the electrode, where you have the corresponding glucose oxidizing enzyme is present, and we will be producing here not water, we will be producing here hydrogen peroxide, H2O2. So, production of that hydrogen peroxide can be sensed by this electrochemical technique. So, what do you see now, that how we get the CV, that means the cyclic voltammetry, how we measure, how we record, and what are the corresponding cell arrangement for this. So, as we were started our discussion that two electrodes, one is working electrode and the reference electrode is not sufficient. So, we must bring something over here for getting CV. We need 3 electrodes. So, you will have a system which is having 3 electrodes. So, already we have working electrode, the reference electrode. Now, we will bring the third one as your counter electrode or auxiliary electrode. So, it will be counter electrode or auxiliary electrode. As we basically what we discussed, that as we promised, that we will not allow to pass any electron or any charge or any current to pass through the reference electrode, because that way it will not be, if we pass current through reference electrode, the meaning of using reference electrode to monitor the working electrode potential would be meaningless. So, we will not allow any current. Now, we are bringing counter electrode. So, this will be the sink basically to allow this particular current to pass through this electrode. So, this auxiliary electrode or counter electrode, it can be a simple platinum wire sometime, a simple platinum wire which is dipped inside that particular cell or the electrochemical cell. So, the entire current will be passed through your counter electrode for this type of measurement. So, we can measure the current as well as we can measure the potential. Now, we will see how we can plot that and how the arrangement is. in terms of the corresponding placement of the electrodes, what is written in the different books, and all the informations what we gather from any other sources. So, CV is nothing but a current response of small stationary electrode in an unstirred solution. So, these are the basic conditions, that solution should not be stirred, is not agitated, whatever there in the rest state, that means unstirred solution. Initially you can start the solution, we will start basically, we stir for half a minute or a minute, then we stop the stirring, then we switch on the thing for measurement. So, unstirred solution is there and is getting the corresponding excitation from the waveform. As we have discussed already, we categorize the thing as triangular voltage waveform. So, the triangular waveform is required, and this is the connection we have. What we have? We have electrode 1, electrode 2 and electrode 3. So, that gives rise to the corresponding 3 electrode system for cyclic voltammetric measurement. So, this is most important thing, that you can given this typical block diagram for that also, and you can be asked to level the different parts, which is A, which is V, and what are the 3 electrodes, and where the corresponding external source for the measurement is available, because everything is your electrochemical cell. That means you require the voltage from here from external source. So, as the diagram tells, this is A and V, and basically what we will be looking for, also do not forget this also, that current is nothing but your A and V is your potential. So, sometimes not only we consider is as the current voltage plot or current potential plot, you can consider as the current voltage plot. Also we can consider as the AV plot, or also we can consider as IE plot. So, these are the names for your CV. We can have these plots. So, anything can be asked to you. You should be very much careful at this point, that it is the current potential plot, current voltage plot, AV plot, and this corresponding IE plot. So, what we get therefore, that 3 electrodes and 2 measurements. So, it is typically a 3 electrode setup you have, where number 1 is your working electrode. So, working electrode is directly attaching to your source, but is also giving rise to the connection for your measurement of your potential. So, you have the corresponding one is your 3. So, as I told you that the working electrode is measuring your potential, E is being measured or V is being measured. So, V is being measured. So, as I just see that working electrode is responsible for the measurement of V. So, this is one such circuit. Then we require this third one is for your reference electrode. So, reference electrode and the working electrode is measuring your potential, and the counter electrode and your working electrode, so this is also connected. So, this is one circuit and this is another circuit, and this is your solution. So, within the solution you dipped 1, you dipped 2 and you dipped 3. So, all 3 electrodes are inserted within the solution, which is electroactive in nature, and you have 2 electrical circuits. So, 3 electrodes and 2 electrical circuits you require. One circuit is measuring your potential, that means the voltage V, and another circuit is measuring your current A or I. So, that is the most important technique what we can have, and the output what we get is like this, and any standard textbook have this sort of plot, because this is well known plot for your cyclic voltammetric measurements, and this typical cyclic voltammetric measurements what you can have is very important, because point wise we can have, is not that you recorded the data like your potentiometric titrations, because this is also you can consider as some sort of titrimetric method. When you have only linear sweep, you get up to this point F only. So, up to this point you get only one sided thing, that means whether your system is oxidized or your system is reduced. So, this particular waveform, which is not a triangular one, is a linear waveform, can give rise to a response from A to F. So, is A to F. So, this is your linear sweep, linear scan. You get A, B, C, D, E and F. Okay. So, what you see that corresponding one, that means with respect to the time, what basically the instrument is looking for us, instrument is measuring for us is nothing but your corresponding measurement of your potential with respect to time, because what instrument is giving, we get the corresponding one. We know that is the potentiostat as well as the galvanostat, which is measuring the current. So, the combination of these things based on complicated, not much complicated nowadays, is a very basic electronics part on operational amplifiers. So, operational amplifiers are making our life easy such that we have automated instruments, and these automated instruments are also giving advantage by measuring all these in computers. So, computer terminal is fine to record these voltammograms. Earlier we are using XY recorders or oscilloscopes for those measurements. So, here what we find that these typical measurements, so when we move from A to B, you see the linear sweep is like that. So, when we move from A to B is not changing much. So, the potential what we are going from B to C, because A to B is a very long scan, but B to C is not very much, but you see the current is increasing like anything. B to C and C to D. So, this particular range, the whole current is increasing, but your waveform for potential is changing linearly. So, if we get this for this particular type of scan, A to D will getting, so at D will be reaching the maxima. So, the maximum what we are reaching for the plot is D, then as it is scanning till F, your current is decreasing. So, is basically the corresponding thing that some electrode processes are taking place. That means, the available concentration on the electrode surface, which is electroactive, has all been reduced if we consider, or all been oxidized. So, if we consider that this is the corresponding potential for your oxidation or the reduction, but if it is a corresponding one for your value, what we see is your cathodic peak potential. So, cathodic peak potential is for your reduction. So, if you get that as the reduction potential, so you get the immediate reduction. So, everything will be exhausted. So, no more reduction. So, your current will decay in this fashion, that means a typical Gaussian shape of decaying is there till you reach the end point F, where we automatically the machine will switch off to go for a cycling process. That means, A to F is the maximum one. Is maximum one is nothing but plus 0.8 to minus 0.1 volt. This is minus 0.1 volt. So, as your potential is scanning from plus 0.8 to minus 0.1 volt, we get the response. So, this upper part of the plot we get. So, as we go back again to that starting potential of 0.8 volt. So, going to the starting potential of 0.8 volt, what we get that your thing will now change, and again we have the points, but now the points are marked differently. One is as G. So, when it is G, the time potential plot will give you the corresponding time, and the potential current plot will G will come over here. Then you have H, I, J and then K. So, the whole cyclic process is completed and we get this particular plot, and how we use to extract out the informations out of this plot, that we will see. And this one, the plot has, we have discussed that what sort of waveform you put to the electrode system is a 3 electrode system, and the corresponding potential what is being applied to all these electrodes, particularly the working electrode, because this potential is applied to your working electrode with respect to the reference electrode. So, potential versus time waveform is look like this, and we have the cyclic voltammogram. So, this is the typical cyclic voltammogram of a very small concentration of potassium ferricyanide. So, is a 6 millimolar concentration of potassium ferricyanide what you have in your hand, and that 6 millimolar solution, that means 6 into 10 to the power minus 3 molar solution, and usually we go for simply the millimolar concentration. So, you see that millimolar concentration and the cell volume is also very less, because we require a very small concentration of this material, because the cell volume is only 10 ml. Sometimes it can go down to 5 ml, even 1 ml. So, a solution volume of 10 ml is fine. So, your required concentration to get this concentration of 6 millimolar you can find out. So, how small concentration of potassium ferricyanide is you require to get this response, and all these informations related to a very electroactive species, because ferricyanide is a standard material for our reference material. Once instrument is installed, if you installed a new instrument, the first thing what your engineer will ask you, that you give me some amount of some reference material. So, this material is available for any lab, for any school lab, any college lab or university lab or any other institutional lab. Ferricyanide is a chief molecule. You have this particular lab material. So, this is your standard material. There is no need to have any costly material to standardize that thing. But thing is that initially what you are establishing is that we are establishing everything, whatever is written over there, one thing is missing, is not written over there, is your medium of measurement. What is the solvent? So, since it is a potassium salt, as we all know that most of the potassium and the sodium salts are highly soluble in water. So, definitely it will be in water. So, the measurement is taken in water, and you should always be careful about all these information, all this very small information, because the voltammogram is shown, is leveled with nicely with the material, and is other thing which is attached to that, and one thing is missing. Sometimes it can be deliberately missed to test your eyes, test your information, test your understanding, that whether you can see that a voltammogram is doing only on the solution, because it can be done on the solid state also, but right now what we are doing in solution phase. So, the solution technique, and we are inserting everything in solution in the electrochemical cell, inserting these 3 electrodes. So, one is in the millimolar range of 6 concentration millimolar, 6 millimolar concentration of your electroactive species, which is potassium ferricyanide. Along with that, we add 1 molar of potassium nitrate. So, you see the times of concentration what you require to add for the measurement is your potassium nitrate concentration. So, this potassium nitrate concentration is known as supporting electrolyte when you go for your measurement in water medium or aqueous medium. So, not that the entire thing, that means the electrolyte you require, because the medium should be sufficiently conducting, electroconducting. So, that is why we bring this one as supporting electrolyte to carry the electronic charge entirely by this, not by your electroactive species potassium ferricyanide. So, always we require a supporting electrolyte and the analyte. So, what you have, the supporting electrolyte and the analyte concentration, but if you go, since the medium is not told to you, so what you do, that if you go from water, and if I want to measure this in some non-aqueous medium, which is acetonitride, MECN. So, in MECN also you can have some compound which is your analyte or the reference material to test the machine to see the corresponding response, and the supporting electrolyte. So, since it was K3 FeCN6, and we all know this is soluble in water because this is potassium salt and the supporting electrolyte is KNO3. So, what synthetic manipulation you can understand, you can think of to go for similar type of compounds which can be soluble in your non-aqueous medium, which is acetonitrile. So, very simple thing that, as I told you, as I was mentioning, that it is the potassium salt, the solubility of these salts in water medium is responsible for your potassium salt. So, if you are able to change these potassium salts by some cationic part, organic cationic part, which should be soluble in MECN. So, what organic part you can think of? We can think of the typical organic base like NBU is the butyl group. So, N instead of NH3 we have NH. So, NR. So, NR3 is tributyl amine like ammonia. So, tributyl amine. Then you can make some cation of it, which is NBU4, which is normal butyl, and which is definitely a cationic one. So, tetrabutyl ammonium ion. What you require is your tetrabutyl ammonium ion, and that tetrabutyl ammonium ion can replace these potassium ions. So, you will get the corresponding tetrabutyl ammonium salt of ferricyanide and the tetrabutyl ammonium salt of nitrate, that can be very easily useful for your analyte or the reference material or your supporting electrolyte for your cyclic voltammetric measurements. So, we measure all these, and this potential waveform we can correlate with all these points, and what we see that this can be very much useful for your understanding of the medium as well as the relative concentration of the material or the analyte as well as the supporting material. So, anywhere we can apply this particular thing, you should be able to indicate that this is the corresponding process of cyclic voltammetric measurement, and we start from here, start from here. So, that is why this arrow is shown to you. So, this is your scan direction. So, you have to give the arrow all the time, not only the forward direction, but also we sometimes give the backward direction. So, we are ending. So, we start from A and we end to K. With respect to the time, it is A and we are ending K to again to 0. So, that gives rise to a typical cyclic process, but is electroactive. So, next day we will be considering from here basically that what are these IPC, IPA, and how we measure, how we get the right information what we are looking for. The most important information is your E0 value or the EF value for the process or the electroactive species which is undergoing oxidation or the reduction. Thank you very much.